Okay. Some reason the streaming is not working. Just give me 1 second. Yeah, is anyway. This that would be good. Okay, I'm live now. Yes. So, like I was saying, so we'd be talking about the name reactions today. Let's get started. See, these are the type of name reactions. Those are actually not mentioned in the book, but you have gone through these reactions. You know about this reaction, so they are completely authorized to give these questions as well. They are not authorized to mention this name reaction, like which of the following is, let's say, Schwartz reaction, which of the following is Finkelstein reaction or Brinbaum-Simonini reaction. They cannot really ask you that question, but they can give you as an option. You have seen those kind of questions, right, while solving the question. Okay. So that is what we are going to do right now. So, all right, would be learning about, and the processes that we have already learned, would be going a little bit deeper in that things. So the first reaction we'll be going for is the Groves process. So today I'll be completing the haloalkanes, all the name reactions out there. So we'll be starting with the Groves process, and we all already know that the Groves process is the first name reaction out there in the haloalkanes, where what we do is, let's say we have an alcohol like CH3, CH2, OH, with the help of HCl, halogen hydrocide, and anhydrous ZnCl2. And anhydrous ZnCl2, what happens is, if we do this reaction, we'll be able to see that water goes out of the system and we get CH3, CH2 here. That's the final product that we get from here. Now, there's a lot in this reaction, actually, a lot to learn about it. So first of all, what is the reason behind this anhydrous ZnCl2? So what is the reason behind this? I guess you know the answer, right, Shini?
It acts as a Lewis acid, I guess.
Yes. So why anhydrous ZnCl2? It acts like a Lewis acid. So over here, what happens is, when we are making this reaction happen, let's say CH3, CH2, OH, the mechanism goes like, when the ZnCl2 is given to it, ZnCl2 actually acts like a Lewis acid. Now, what do you mean by Lewis acid? The ones who accept electrons, they are called Lewis acid. So the lone pair of oxygen is what? Going to make a coordinate covalent bond with it. And you'd be getting an intermediate which would look like CH3, CH2, OH, ZnCl2, and there will be a plus charge on it and a minus charge on it. So this is actually the intermediate behind this reaction. All right. Then what happens is, the Cl minus from HCl comes and attacks over here and takes it out. This is what we think. But later on in the mechanism, today only we will be talking about that. We would know that this is not really an SN2 reaction. Right now, the way I have shown you, it looks like an SN2 reaction, but in reality, it is not an SN2 reaction. It is, what is it then? SN1.
SN1.
SN1. Now, how do we know about that? So right now, if you look into the NCERT, it is written that if you do this reaction, let's say CH3, CH2OH, if you do this reaction with HCl, you would need anhydrous ZnCl. Okay. To get the product. If you take a 2-degree alcohol, it is clearly mentioned that the reaction with HCl and anhydrous ZnCl2, this also gives you a product. What is the product am I going to get? I'm going to get CH3, EHCl, and CH3. And this reaction is actually faster. And if you do the reaction with a 3-degree alcohol, in case of 3-degree alcohol, you don't even need anhydrous ZnCl2. The reaction happens without anhydrous ZnCl2 as well. So just give HCl and you would get your product. Again, what's the product? What the product would be, just the alcohol would be substituted by chlorine. So which gives you the idea that more you are going towards 1 degree to 3 degree, the use of the Lewis acid is not needed anymore. That means the reaction is getting faster and faster. So it's clearly understandable that 3 degree is the most reactive, then 2 degree, then 1 degree. This order, which is written in the NCERT, that 3 degree alcohols, they are the most reactive for Group's process. This is what tells us that this reaction actually undergoes SN1 mechanism. So there's the carbocation getting formed. That's why 3 degree is the most stable, then 2 degree, then 1 degree. So this is the exact order of the Group's process reactions. All right. With respect to substrate, with respect to the alkanes, this is the order. Now, what would be the order with respect to the halogen hydracids now? So let's say they're asking, in this process, if I give HCl, if I give HBr, and if I give HI, so try it. Which one would be faster, or which one would be the fastest out of these three? Would it be HCl giving the fastest? Let's say I'm taking a common substrate now. Then which one would be giving you fastest reaction?
Or is it HI?
And why is that?
But I minus big size, the better nucleophile.
But again, it's an I minus is a better nucleophile. You were right before, but then again, it's a SN1 reaction that we are talking about. So any which ways, your answer is correct. HI gives the highest reactivity, then HBr, then HCl. Now, why is that? Because it's a pretty simple thing. Because let's say, in order to make this reaction happen, HI has to break into H plus and I minus. HBr also has to break into H plus and Br minus. And HCl also will have to break into H plus and Cl. We already know that in HI, the hydrogen is using its 1s orbital and iodine is using its 5p orbital. So there's a huge orbital mismatch which is working there. So breaking into H plus and I minus is comparatively easier in this, out of all these three cases. So because of orbital mismatching, mismatch, formation of nucleophile is most feasible for HI. So that is the reason why HI has the highest, then HBr, then HCl. So if you just see the reactivity, it goes like, let's say you have a common substrate. If you make the group's reaction with HCl, okay, you need ZnCl2 and you need high temperature in there. But if you just give HBr, then you don't really need ZnCl2. You just give HBr, and this reaction would happen in room temperature. And if you give HI, you just have to reflux. This reaction would happen. So as you can clearly see that more you are going down towards HI, the reaction conditions are getting milder and milder. That's why HI with HBr, we need a little bit of H2SO4 as well. Okay. We don't need ZnCl2, we need a little bit of H2SO4. But for HI, we just need to make a reflux with it. And that's what keeping.
What's the meaning of a reflux?
What is the
meaning of reflux?
Reflux means something like heating it a little bit with a very little amount of temperature. Okay. That is what reflux is. Now, this is what has been mentioned in the NCERT, but now, right now, I've just extended a little bit. As groups process is mentioned, there is one variation of group process out there. That is what I'm going to talk about right now. So let's say they can also ask this groups process question in this way. They would go like ROH plus KBr plus H2SO4. Guys, this is another variation of groups process. KBr and H2SO4 together would make HBr. So it is the in situ formation of HBr. This would also give you RBr in here. Similarly, for RI as well, we can also make in situ RI by Pi and H3PO4 or H2SO4. H3PO4 is the exact acid. That would also give you ROH, sorry. That would also give you RI in here. So these are the two variations where you can make the molecules, make the reagents in situ, means inside the reaction medium. One more thing, always remember, this R group has to be an aliphatic hydrocarbon. Aromatic hydrocarbons like phenols cannot undergo group process. Why is that? Because in groups process, what did I tell you? What is the intermediate there? It's an SN1, so it's a carbocation intermediate, right? So carbocation in a phenyl system is never stable. This is not stable. That's why this reaction cannot undergo the groups process. So if you want to get aryl iodide, I'm going to tell you what is the exact mechanism of it, which is actually the best mechanism of making aryl iodide is actually our what did I tell you the name of the reaction is? Huntsdiker. Huntsdiker reaction is the best way of making the alkyl iodides. So, but right now, just remember, aromatic alcohols do not undergo this particular reaction that happens.
Now, can we also use diazotization for making aryl iodide?
We can, but like I said, the best way. So best way means which takes it's very cost efficient. It's very much less time consuming. Considering all this thing, the best way is that one. All right. So I guess I have talked about all the things which were needed here. Fine. Now coming to the next named reaction, which is known as Schwartz reaction. So I guess we do know what is the Schwartz reaction. Do we?
The formation of fluoroalkane.
Formation of fluoroalkane, right? That's right. So how do we really do that?
The alcohol is treated with AgF or any other D block fluorides, then get a fluoroalkane.
That's correct. So this reaction is also known as halogen exchange reaction. See, not only fluoroalkane, Harshini, even iodoalkane is also being formed by halogen exchange method. That reaction is known as Finkelstein reaction. Okay, but that is not really mentioned in your book, so I'm not really going into deep in there. But Finkelstein is the halogen exchange way of iodination. Fluorination is the best way, best actually. So what we have to do is we have to take any halogen. Then we have to make it react with any D block fluoride. Why is that? Because D block fluoride are fluorine donors. So you can use AgF. What else? Ag2F2, right? And SbF3, SbF5. All of these are fluorine donors. So Schwartz reaction doesn't mean that only Ag2F or only AgF. These are all fluorinating agents. So anytime they can give you a question, like let's say you are learning right Hg2F2 with Hg2F2, it is source reaction. For both, it is fine. But let's say when you are going to give NEET, they would make sure that they ask you question from SBF5 because they know that you are not going to learn SBF5. You are going to learn the easier way. So definitely most of the people right now would be going for HGF. That's the easiest way of recovery. But we need to remember all the things because that is what they're going to look at. All right. So,
Sir, what makes the D block fluorides better fluorine donors?
So actually what happens is when we are going for the D block systems, D block systems are very, very unpredictable because of their high Z star present in them. To know that for D block elements, the D orbital being present in there, what happens is they are not really being able to screen the nuclear charge, right? So because of their high nuclear charge, what happens is their bonds are really very unpredictable. So what happens is when you go for a normal fluoride, the bond with fluorine is pretty strong. But when you go for the D block elements, because of their high Z star, the bonds, they are not really that strong like that, the normal metal fluorides. That's why D block fluorides are comparatively more breakable that you can consider. All right. So anyway, what happens is we get the fluorinated product in there. And like I said, similar way we can do iodination as well. That thing is known as, if you want to just write it, you can write the name in there. It's called Finkelstein reaction. Finkelstein. Not really important, but there is no harm if you just know the name. Okay. So that was the Finkelstein reaction in here. Now, by the way, for fluorination, why do we need the halogen exchange method? Because fluorine is not really very easy to control, right? So that's why we need a halogen exchange method for this. One more thing, there is one connecting topic of Schwarz reaction. And my Balzschumann over here, this is also a kind of a Schwarz reaction type of thing, but this time it is in the aromatic systems. This is really very important. So what happens is, let's say you have a diazonium chloride, so benzene, you have aniline. Now from aniline, what is the reagent for diazotization?
HNO3.
HNO3, are you sure?
Sorry, HNO2.
HNO2, and how is the HNO2 being formed?
NaNO2 and any H2 suppose any concentrated HCl.
HCl, NaNO2 and HCl. So that together they make HNO2. Now, I guess I told you in the classes that HNO2 can be given in so many different ways. They can go like NO2 minus. They can go like ONO minus. All these things are same. All right. All the things that are trying to tell you that they are giving HNO, nitrous acid. Now, this by giving nitrous acid, what we call 0 degree to 5 degree centigrade temperature, what we do is we form the diazonium chloride. Okay, we get the diazonium chloride. Now here what we have to, so far the Balzschumann reaction haven't really started. From here what you have to do is you have to give HBF4, fluoroboric acid. If you give fluoroboric acid, then what happens is N2 plus BF4. This is the intermediate getting formed. Now then again, when you're going for your boards, you feel like this intermediate is a little bit difficult to draw, so let's just skip this. But always remember that whatever you feel like you want to skip, they know that already. But this is what most of the students are skipping. And if you are practicing much and much, that many questions, then you right now you do know that the intermediates are really a very hot topic from where they like to ask questions. So because they're unpredictable. So this is what they get from here. N2 plus BF4 minus. Now here what happens is an HCl is the byproduct, I guess that is understandable. Now this molecule, if you just heat it, then it becomes fluorobenzene. Okay. This reaction has another utility as well. Do you know what would happen if I give NaNO2 in there? Try it. This is there in the chapter amines.
Where nitrobenzene is formed.
That's correct. Nitrobenzene. This is a very important process for boards as well. Formation of nitrobenzene. Okay, so that was the Balch-Simmons reaction. That is kind of a variation of source reaction. All right. Now, coming to the Hunsaker reaction. Now, what is the Hunsaker reaction here? So we start with the silver acetate. Okay. Let's start with the silver acetate molecule. So how can we really form it? Let's say they are trying to trick you with the formation as well. So what you have to do is they would give you like this. They would give you an acid, and they would give you a base of silver, like Ag2O or AgOH. So acid with AgOH would definitely make salts and water. So silver acetate, salt, and water. So just take carboxylic acid with AgOH or Ag2 or any basis made by silver. Then what would happen? You would get silver salt. Now over there, if you give bromine, and if you do reflux of this, any halogen would do, bromine would do, and chlorine would do, but not iodine though. But anyway, bromine, chlorine, if you give any one of this, then first what happens is, see, let's say this is Br2. Now this is something a little bit tricky in here. Br2, when it is breaking, it is supposed to be broken in homolytic cleavage because it's a similar atom. But as you can see, if they get broken as Br plus and Br minus heterolytically, then what happens is Ag plus takes this Br minus and forms AgBr. So if you want to ask me, so why is it breaking as a heterolytic level? The reason is silver. Silver is actually, kind of influencing this heterolytic cleavage in here. This influence is not the first time that you are seeing. Anytime when we have done this radical mechanism, all the single time we have learned that a particular reactant can actually influence the bond breaking. So here the same thing is happening. This silver is actually influencing this bond breaking. What have you seen similar kind of a scenario? You have seen this same scenario in the Cl2 FeCl3 situation. In Cl2 FeCl3 situation, whenever you used to do chlorination in benzene, remember you used to do Cl2 FeCl3 in there. Now, what is Cl2 FeCl3 actually do? See, chlorine is supposed to be broken as a homolytic cleavage. But the moment you are giving FeCl3 or Lewis acid in there, what actually happens is this FeCl3 is breaking now as a heterolytic cleavage. Now, what is the reason behind this? Because now FeCl3 takes this Cl minus and becomes FeCl4 minus. Just for FeCl3, just so it can become FeCl4 minus by to make its octet filled up. It is influencing the Cl2 to break as Cl plus and Cl plus. So the same thing is happening here as well. So this is not the first time we are learning this. All right. Now, I'll just stop this thing up. Now, what happens is it would make AgBr, so the Br minus is gone. All right, the Br minus is gone, taken up by the Ag. So what are the other things that I have? I have a CH3 COO minus and a Br, so they would combine together and I would get this. Is that clear? Now, in this situation, oxygen and this halogen, whether it's chlorine or whether it's bromine, they are actually close. Their electronegativities are not that much different. Always remember, to make a bond heterolytically clipped, the electronegativity difference has to be 1.7 and beyond. 1.7 is the minimum value. From 0.25 to 1.7 is the minimum value. That is the electronegativity difference you need to break a bond in heterolytic cleavage. So as the bond difference, the electronegativity difference is not that much in between oxygen and bromine. What happens is this molecule is now going to break as a homolytic cleavage, and you would make a radical in there. So this is the free radical that you would form. All right. Now, this free radical now would initiate this particular mechanism that you can see right here. So what happens? This free radical is first breaking this carbon-carbon bond into homolytic cleavage, like this and this. Now, what would be the benefit of that? If I break the bond as homolytic cleavage, that would be a radical here, that would be a radical here. Now, these two radicals, this free radical and this free radical, would make it CO, and I get CH3 dot A here. Now, again, are we seeing this kind of cleavage for the first time? The answer is no. We have seen this before in class 11 hydrocarbon. There was a reaction called coal-base electrolysis. There we have seen this happening. Class 11 hydrocarbon coal-base electrolysis. Do check it once if you don't remember this. So you get CH3 radical in here. Now, to remember, at first this bond got broken as COO radical and Br radical. That Br radical is still there from this Br radical. That Br radical comes now and make it CH3 Br. So that's how, guys, we get a step down reaction. So a decarboxylation is happening. The entire carboxylic acid groups is gone now, and we are getting CH3 Br. Now, in the meantime, let me check how is the streaming going on. Yeah, great. I think it's fine. All right, but I told you before I started this, we can do it for bromine and chlorine, but not for iodine. Because if I do it for iodine, it won't be Hunts-Dicker reaction anymore. It would become Brin-Bum-Simonin, that reaction. So what actually happens over there is, let's say, let me see, is the red color visible that much? No. Just a second. Just zoom in. Yeah. So what happens is, if you start with silver acetate, and there, instead of bromine or chlorine, you give iodine in presence of CCl4 and reflux. CCl4 is a solvent, okay, on this reaction. What happens is, it doesn't make the CH3I here. It makes an ester rather. This is the product that you get from iodination. Again, we are not really expecting this question to come, but as you are learning this, let's make sure if this kind of a question comes when everyone else would fail to answer these questions, we would be there to answer. See, they cannot really ask you what is the Brin-Bum-Simonin in there. They cannot really ask you this question, but they can do this. They can give you a question. There will be 4 options, A, B, C, D. In those options, they can go like this particular name. Then at that time, you'd feel like you don't even know about the name. So generally, this is psychology. What happens is, when we are giving an exam like NEET, when we are so nervous, at that time we are actually more prone to leave a question than solve a question, because we are all the time we are just thinking, because our teachers have told us that all the time we are just trying to think, like, if this is a question that can give me a negative marking, I need to leave it right away. So the moment we see something like this, and when the moment we see like there is a question where the names are not really like known to me, we just try to leave this question right away. So that's why we are learning this question. So if you just start with 2 molecules of silver acetate, you get the ester as a product. You don't give the iodide. Is that clear?
So can you please repeat the name of the reaction for the iodination?
Okay. All right. Yeah, screen is also going good. Achha. Now, the next topic is, it's not really a name reaction, but there is something that we need to know. So like I'm trying to keep all the exceptional kind of things as well while teaching. So in haloalkanes, halogens, you have clearly seen that rather than the name reactions, there are more questions on optical isomerism and stuff. So there are not many questions that you can find from the name reactions though. But this is something that I guess you have seen in the NCERT. Okay. But I don't know how many of you have paid that much of attention while solving this kind of question. So iodination. Whenever you try to do iodination, we specifically need an oxidizing agent for that. So let's say we are trying to do iodination in a particular molecule. This can be a benzene system, it can be an inorganic system, anything. Whenever we are, let's say we have a CH3I molecule. Okay. If I, sorry, CH3, just a second. Just a second, it's got hand. Yes. Let's say I have a CH4. What's going on? Let's say I have CH4 and I'm adding I2 with it. Okay. So guys, this is also a kind of a radical mechanism that you have to go through. I guess this is there in the NCERT, so you know it. So you would get like CH3I, and the same thing happens if you do it from with a benzene ring systems as well. All right. But this particular reaction that I have done, this reaction is actually reversible. This reaction is actually reversible. Now, why is that reversible? What is the basic reason behind this? It's actually this HI bond, like I said, this bond breaks very easily. Like H plus and I minus, it breaks very easily. So the reaction can go back as well. So now what do we need to do in order to stop it from going backwards? So what you have to do is you have to remove the HI from the system. So shouldn't you know what you have to do in here? Make that happen?
Oxidize to I2.
Mm-hmm.
When we oxidize Hi to I2, then
yeah, how do we do that? What are the agents that we do for oxidation?
We should not use sulfuric acid, but any other oxidizing agent.
Like HNO3 would do the work. HiO2 would do the work, hydroiodic acid. What they would do is they would actually convert this HI to IT and make it a reversible, I mean the cyclic reaction. By these processes, we can make it simple. Right. Now, these are, I guess, something that is there in the last chapter, which is the amines, but we have it in haloalkanes as well. We have it in alcohols as well, and aldehydes as well. So that's why I picked this up. Sandmeyer's and Gattermann's reaction. So before I start talking about this, I do want to know which one of these two is more advanced out of them. Like, is it Sandmeyer or is it Gattermann? Which one is more advanced?
Where is it Sandmeyer because it gives more yield, like more products of form.
So what was the reagent for Gattermann then? And what was the reagent for Sandmeyer?
For Sandmeyer, it was copper chloride, like Cu2Cl2. But in Gattermann, it was copper separate and HCl.
Yes. And so what are we changing there actually? How is Sandmeyer, like, he's not really doing anything, isn't it? He's just keeping the copper there, he's keeping the halogen there. So what is it changing so that the yield is getting in the higher end? What he's doing actually is he's increasing the surface area. So he's giving copper powder, right? By giving copper powder, what happens is he's increasing the surface area of the catalyst. So let's go for them one by one. Okay, Gattermann and Gattermann-Koch are not the same thing. I'll talk about both the things as we speak. So Gattermann is when you have a benzene diazonium system. When we have a benzene diazonium chloride, and over there, when you're giving Cu2X2, then what happens is you get the X on the benzene. But then again, the X is only Cl and Br. How do we convert it into I? By giving Ki. Remember this. For iodination, we have to give Ki, not Cu2I2. For fluorination, how do you do fluorination?
Where HBF4 is given.
HBF4, yes, that one. All right. Now, pulsion. So right now, X is only Cl and Br. So what was I talking about? Cu2X2. That is what you need in there. When they talk about Gattermann-Koch, that was there in aldehyde ketones carboxylic acid. Do you remember what was the Gattermann-Koch?
When benzene is directly converted to benzaldehyde.
Benzaldehyde. And with what was the reagent in there?
Carbon monoxide, HCl, and Lewis acid like AlCl.
That's correct. And what was the intermediate there? Right. Try to find it. What is the intermediate?
So is it CHCl2?
No. CHCl2 is the intermediate. It's not only CCl2, it is CCl2 carbon, the dichlorocarbon. It's the intermediate of rheumatics. You need chloroform for that. So first, when they react together, what would they form? CO plus HCl, they would form HCOCl, isn't it? Now tell me what would happen with AlCl3 when they react. What do AlCl? What is AlCl3 here? Lewis acid. Lewis acid one more time. So what are the works of Lewis acid? Why are they Lewis acid on the first place? Because they have incomplete octet, right? Al, Cl3 has incomplete order. That's why we call it a Lewis acid, because it wants to take electron. So what would it do? It would break this bond molecule into HCO plus and AlCl4 minus. So this is the intermediate, HCO plus. Okay, so now what would happen? This HCO plus would be taken up by the benzene ring. That's why we get the PHO directly. How is the HCO bond? HCO molecule looks like HC double bonded O then plus. Okay. So that is how we get the cation. So
Is there any
again,
name for this intermediate ring form?
you can call it formylium ion, but it's actually, you know, when you have a CH in there, we call it acylium. As this is not acetyl, not from acid, it's like H. So we can call it, you know, formylium ion. All right. Now, yeah. So what was I talking about? The Gattermann's reaction with Cu2x2. With Cu2x2, it is Sandmeyer's, right? Cu2x2 is Sandmeyer. Gattermann which is Cu1. The modified is Gattermann. This is Sandmeyer. Then the Sandmeyer reaction got modified by Gattermann. So Gattermann's reaction was like everything was same. He made double M. Gattermann. So everything was same. Only the changes. Instead of Cu2x2, you give copper powder and copper powder and extra. That gives you the same problem. All right. So that wasn't there. All right. Then comes another name reaction called Mendius reaction. This Mendius reaction is actually there in the NCERT. Have you ever noticed it? The Mendius reaction. It is actually there, but they are not giving it as a heading. What happens is, if you open the chapter aldehyde ketone carboxylic acid, in that chapter, if you go to carboxylic acid, do remember in carboxylic acid, let's say if you open the chapter, you'll be able to understand under the section of oxidation. Just a second. Malfunction a little bit. If you go to the navigate to the section of oxidation, you'd be able to see generally whenever we take an alcohol, how do you oxidize it? By K-4, K2Cr2, plenty of them are there. All right. Then we have like all those CrO3 and all those things. But you would specifically see in there, along with K-4, K2Cr2, right there in the bottom of the arrow, they would be writing in a very short, small hands CrO3 H2SO4, and they would be calling it Jones reagent. In the same way, when you would go for like the reduction over there as well, you'd be able to see the Mendius reaction is given in there. So if you write, if you start from under the section cyanide, you'd be able to see as well. So what happens? It's just a reducing it. The Mendius reaction is nothing but a reducing it. Sodium and ethanol. Okay. This reagent is there, but maybe they're not mentioning it is Mendius reaction, or maybe it is written. You just have to check it there. It might be written, it might not be written, but it is there 100%. So when the reagent is there, so they are definitely they can give Mendius reaction name, because you should know the name of the reagent, and they do know that most of the people, they do not really know the name, so they can use that trick in there. So let's say you have cyanide. If you give sodium and ethanol, it is a very good reducing agent, and you would end up in CH3, CH2, NH2. Mendel's reaction is just a substitute of lithium aluminium hydride or sodium borohydride. The next class is actually what I'm going to do is I'm going to like finish this name reactions by chapter. So right now we are going to complete all the possible name reactions in haloalkane, haloarenes. Then we'll be going to the alcohols, then the aldehydes, then the amides. After all those things are done, I'll be specifically taking another session for just the reducing agent. Which one is the best reducing agent, then how the reducing character is decreasing, who can reduce whom. Like hydrogen, nickel, platinum, palladium, they can reduce double bonded systems. But then again, if you go to a double bonded O, like ketone system, in there to reduce them, you need lithium aluminium hydride, sodium borohydride. But again, lithium aluminium hydride, sodium borohydride, they cannot really reduce an alkene to alcohol, in alkene to alkane. These things they cannot do. So like how many different reagents are out there who can work separate? This is just like, when I was teaching in the class, I told you like this. There are different mechanisms for reducing a double bonded O and a double bonded C. Alkene reduction and ketone reduction, carbonyl reduction are not the same mechanism. That's why we have different reducing agents. There are few of them, those who can do both of the things. So we'll be talking about all those things in there. All right. So ketone or a carbonyl reduction and alkene reductions, they do not take the similar reagents. That's why lithium aluminium hydride can reduce ketones to alcohols, but not the alkenes. Although lithium aluminium hydride is one of the strongest reducing. What is the reason behind this, and why is they are not being able to do that? That is something I'll be talking about in the next session. Right now, I'll be ending the session with. Yeah, go on.
So instead of sodium, can any other metal be given along with ethanol?
Whenever we are talking about the name reactions, you have to stick to the exact same metal. As it's a name reaction. Name reaction means that scientist has copyrighted it. Okay, so sodium and ethanol only. And there is no such like, in that case, you have to look into the research articles a little bit. I can make that search for you. But there is no such other metals which is reported so far that can make that happen. But that's not something which is impossible to happen. Like if sodium can do it, potassium is also supposed to do it as well. But then again, without knowing the exact thing, it's not something that I would suggest you to do. Okay. And for name reactions, you should always follow the exact reasons in there. That is something you'd already. Now, Gilman's reagent. Have you ever heard about this? No, right? But then again, this is again another thing that is there in the NCERT, which is given in the NCERT, but just the name is not given. Gilman's reagent is an organometallic compound, just like Grignard. So we have heard about the Grignard reagent before. Grignard reagent goes by the formula of CH3MgPr. Gilman's reagent is actually when the metal is not magnesium, instead the metal is copper or cadmium. That's called Gilman. Just a second. Got hanged again. Gilman's. What is a Gilman? When the molecule goes like, let's say R2Cu Li. Okay. This is also an organometallic compound. How do we really understand what is an organometallic compound? Let's say there's an organic compound. With that, you have a metals connected. That's called organometallic. How do we make Gilman's reagent? First, you start with a alkyl halide. Start with an alkyl halide. Then you react it with lithium. Then what would happen? You'd get CH3LiX, just like the way you get CH3MgBr, MgF, that way. Now, then you react it with copper or any salts of copper. Then you'd get CH3 hold to CuAli. Now, why is it hold to all of a sudden? Because copper's valence is 2. That's why. So this is Gilman's reagent. So what would it do? Just like the Grignard's reagent, it also gives us CH3 minus. Okay, so R minus, alkyl minus, negative. You know that Grignard reagent and Gilman's reagent, and these are the, like, there is another one, Kurehouse synthesis. You don't really have it, but these are the reagents. Those who are only the reagents who are capable of making alkyl groups as a nucleophile. There is no other reactions those who can make that happen. Alkyl groups working as a nucleophile can be done by these elements only. So let's say you have a molecule which goes like CH3, CH2, CH2. Let's give a halogen instead, Br. If you treat it with R2CuLi, what happens is you get R minus from here. The R minus makes SN2 reaction, and you get a product with R on it. That means you can anytime increase the number of carbon by whatever the number you want. If you want to increase by 1 carbon, then just give CH3 whole to CuLi. If you want to increase by 4 or 5 carbon, you just give that much of alkene. So depending on what alkyl group you give, you can literally mix. All right. And then Friedel-Crafts reaction, I guess that's something we all know, but then we need to just revise it a little bit. Let's say you have a benzene ring, or anything in benzene ring would also do. You have a benzene ring. In there are two types of Friedel-Crafts out there. One is alkylation, right? So tell me, what are the reagents of alkylation?
CL3 and RC and Cl attachment.
Yes, CH3Cl and AlCl3. Now tell me, what is the what would be the intermediate in here?
So CH3 plus and AlCl4 minus.
CH3 plus and AlCl4 minus. So it's an electrophilic addition, because see, we do know that benzene is an electron-rich compound. The moment I have CH3 plus, the electrophile in there, the benzene would go and grab it. So I'd get alkyl benzene. Then we have acylated Friedel-Crafts acylation. If you start with benzene, make it undergo the reaction with CH3COCl and AlCl3. We'd be getting acylamine combining together CH3CO plus. Just like formylamine, similarly acylamine, then this would get connected, and we would get acylation. Now this is something we all know, but let's see whether have we gone that deep or not. If I have to make benzene to ethyl benzene, what is the process of doing that? Should I do acylation or should I do alkylation? Simple question. What do you think?
Alkylation.
So the moment you say alkylation, you already know that. I am asking this question because this is not the real answer. So alkylation, if you choose alkylation, see, this is a very good question, isn't it? If they ask you this question and they give you ABCD in NEET, you just go like alkylation straightforward, but that would be 100% wrong answer. Because alkylation gives you polyalkylated product. So on pen and paper, we do make it alkylation, but in reality, if you do alkylation, it would be polyalkylated product. That's why we avoid to do alkylation. That's why the acylation was invented. So what you have to do is, first you have to acylate it. You won't get polyacylated product. I'll be asking you why, but not right now. Now, in here, if you do Clemmensen reduction, I would teach you about this, revise you about this while doing the aldehydes part. Clemmensen reduction, zinc amalgam HCl. It makes double bond O2 CH2. That's the way of doing it. Okay. Now, why acylation is favored? Because when you do alkylation, see, this is so interesting, so logical, that when you do alkylation, you are actually introducing an electron donating group. So actually, that is an activating group. It is activating the benzene even more. If it's an activating group, so it would actually enhance the reactivity of the benzene. So the benzene would keep on taking the CH3 plus if there is any in the reaction medium extra. It would just keep on getting alkylated because it's being activated. On the other hand, for acylation, even if you have extra acylium ions in the benzene in the reaction medium, you would never get polyacylated product because this is a electron withdrawing. It's a deactivator. Isn't it a very nice explanation to this? So we knew about this concept, but this is the best. This is the exact explanation. That's why acylation is favored, because that is actually deactivated. So you cannot go beyond mono products. All right. So this would be the end of the session. In the next session as well, we'll be coming up with this kind of name reactions only and different uses of this, going into a little bit deeper down in there to understand what all possible questions that can come in NEET. So that would be it for today. Okay, I guess we don't have any doubts. All right, then that would be it. Bye.
Thank you, sir.